Okay, tomorrow or on Friday, I hope to give you an assignment. Sorry, it got a little bit delayed, but now it's time to move to the next chapter or next topic. Um, yeah, so this is an important one, and this the concepts introduced today will be a recurring theme throughout. Okay, so uh, so you conduct an experiment and you observe the outcomes, and sometimes you are not interested in all possible outcomes. You are um, in fact particularly interested in consequences of a specific outcome, such as, for example, you are playing some you are involved in some gambling, um, and you may be playing a particular game, say 10 times, and each time, if a particular outcome occurs, and if it earns you money, okay, and maybe if that doesn't occur, maybe you lose some money, and then the only thing that you are bothered about is whether that particular event occurs and how many times, and so on and so forth. Okay, so this can be so. Uh, if ultimately you are interested in whether you are going to uh, win some money out of this game or not. Okay, that's the type of things that you are, I mean, from practical point of view, you are interested in. And so, although you may start with this space, so let me write this. Let omega f p be a probability space. Probability space. So you are not maybe bothered about all possible these things that formulate that form your F, but only some sub collection of it, and that also comes associated with a certain weights. Maybe measures the amount of money you lose or gain, and so on. So this can be formulated, and also thing is, you think of omega as elementary events, okay, as I have been all along using. So for each elementary event, you can associate some weightage or some number, and then if an event occurs, so now that means A occurs. Um, so okay, let me just first before proceeding further, let us say that so a random. I'll explain, yeah, after I write this. A random variable is a function x from omega to r, real numbers. So it is like it assigns to each elementary event a certain number, which tells you your fortune depending on the outcome, elementary outcome. Uh, okay, so that is the way to think of this. But you want to know what is the probability of, okay, a favorable event occurring, all right? And in order for that to make sense, okay, so for example, you may want to know, so let's just say that you are having a coin toss experiment, and if head turns up, you win 1 rupee, and if tail turns up, you lose 1 rupee. And so you want to know what is the so um, so x is equal to 1 corresponds to heads, and x is equal to, so this is just an example, maybe corresponds to tail, and okay, -1. So the thing is, you are if you have a discrete space, there is not an issue, but in general, you would want to know, uh, you would want to assign probability uh, for things like this. Okay, what is this? Okay, now before you can even say this, it should first of all be an event, meaning this stands for some set. What is that set? X is equal to x. So we define. So in fact, it turns out
Hello,
that
sir.
the right thing to do is to look at not just x less than x, but less than or equal to x. Okay, this is the more natural thing to do, and I'll explain why. Um,
Hello, sir.
yes,
Sir, X is a function, right?
yeah. So that's why this stands for some set. Okay, so I'm going
Okay,
to.
okay, sir.
That's exactly what I am going to answer. So let a of x be the set is equal to set of all omega in capital Omega such that x omega is less than or equal to x. Okay, this is for x in real numbers. So if I give you a real number x and I already have my function, so the definition is not complete yet. Okay, there's going to be such that, and then blah blah blah. And this discussion is mainly to motivate what is happening. In the discrete case, it's very easy. You don't need to say anything more. But um, in the general case, you have to say something more, and the reason for that is the following. This is something for which you would like to assign probabilities, right? You are interested to know what is probability of the event AX. What is this? But if this is going to be the case, it better be the case that so this must, so this is meaningless. This is meaningless unless unless a of x is in f. So you put that as an assumption. Okay. Now I will write here that such that an assumption. So in a different thing. So this is what I'm going to write. So now let us write that. So definition, a random variable. I will use the abbreviation RV for random variable x on, so omega f p is a function from omega to x to real numbers. So that's x such that this ax, which is by definition set of all omega in omega such that x omega is less than or equal to little x is in f belongs to. This is something for which you can talk of probability. Belongs to f for all x in real numbers. And we often write ax as the set ax as set of all x equal to x. Sorry, less than or equal to. Okay. Okay. So this is what I wanted to say. Yeah, this is all that is definition of a random variable. I should underline random variable. So a random variable is just a function, and you whatever the thing that you are interested in, that should be an event. Only then you will be able to assign probabilities for that. Okay. So let us do some examples. The first example is actually a coin toss experiment. So suppose, yeah, uh, two coins are tossed. Two coins are tossed, and the outcomes are observed. Okay. Real numbers. So x of hh is equal to 2, x of ht is equal to x of th is equal to 1, and x of tt equal to 0. Okay. Another example, suppose that a pair of dice is rolled, and x is the random variable which computes the sum of the numbers shown.
Sir, could you explain the set AX once in any of these examples?
Yeah, sure. Okay. So what is a of 1? Let us compute what is a of minus 1. Is minus 1, I mean, this is by definition set of all omega such that x omega is less than or equal to minus 1. Of course, that's empty set.
Oh, okay, sir. Yes, I get it now.
Okay. And then a of, let us write a of 0, that's equal to tt. You don't need to necessarily put integer values. Let me continue here. A of 1.5. What is this? It could even be an irrational number. It doesn't really matter. This is, you write it, omega such that x omega is less than or equal to 1.5. And that is, okay, tt, ht, and th. Okay.
Oh, yes,
So
sir.
you can compute it for any x. And if x is bigger than or equal to 2, you get the whole space capital omega. Okay. So you just apply the definition. What are all the events for which x omega is less than or equal to minus 1.
Sir, will our definition be sufficient for all possible subsets of our X of?
Can you ask that question again, please?
Sir, like, will our definition be sufficient in the case where X of omega lies in arbitrary subsets of R? Like A of X is only defined for X of omega is less than or equal to X. So,
no, A of x is always defined for any value of x. Okay, but
yes,
you may get empty set, you may get the full set, you may get a proper subset.
no, like if I want to find out the probability that X of omega lies between two numbers, or like,
That all, yes, of course, everything is possible. Of course, we are going to do such things. Yeah.
like
So
this
it's not
definition
just that, see, these are, that is why it's because, see, they observe that we already, F is what? F is a sigma ring, right? So it will be closed under union. Yeah. So it will be closed under union, complementation, and so on. And if you know the probabilities for each one of these, see, I said that we are interested in computing probabilities of this. Okay, but of course you can play with, see, I play with the axioms of this one, and then okay, you can even. I mean, I didn't want to overload here. You may be interested. You are right. You may be interested in probability of x assuming values between two things. So a less than x less than or equal to b, or maybe you include a here and put less than this, or this type of things. Or you may be interested in probability of x being in some subset of the real numbers, reasonably good subsets. Uh, I should not write some. So, for example, you may be interested in this. So you know these type of things one can do. Yeah, of course. But when you, uh, I just gave the barest sort of. I didn't want to give too elaborate. What are all the type of things you can do with this definition? The motivation for bringing in these sets into consideration is that you are interested in probabilities of certain subsets. Okay,
okay, sir.
that is certain, not maybe not all possible subsets of omega, but certain subsets definitely you are interested in, and the sets that you are interested in arise in a natural way, namely as these type of sets. So that's the thing. Of course, when we work out problems, you'll see. Okay. So what is x here? I'm not going to write the whole thing, but you know, x is a function from omega to real numbers, and what are all the values that it can take? So you see, the let us just do this example. So what is x of 3? X of 3 consists of what? The sum must be 3. Okay. So it could be 1, 2. Oh, okay. Sorry, I should write here A of 3. A of 3. Okay. Of course, I can also compute what is x of a particular outcome, which is a pair, no? So you see, x takes input from omega, which consists of a pair. So let us say 5, comma 3. Of course, that will be 8. Okay. And what of a of 3? If you like, you can write, of course, a depends on capital X, but once given capital X, I'm not going to write here a suffix X, overload the notation with a and so on. So it is, let me write it here, just it is all those I comma j such that I plus j, that's a sum. Okay, less than or equal. So if you want, I can write one more step, is equal to set of all those such that x of I comma j is less than or equal to 3. Okay, but this is same thing as I comma j such that I plus j back. That's what it does, right? X is a random variable which computes the sum. So if you input I comma j, it returns I plus j, and that must be less than or equal to 3. And now you know what this set is. Is now very simple because I and j are bigger than or equal to 1 and at most 6. So you can write that 1, 1, 1, 2, 2, 1. That's it. Okay. All right. So, yeah. Let me give some different type of example. See, you may have played this game of dart. So you have this dart board, and I'm going to sort of slightly simplify the model for you. Center is O, and you just throw dart at it, and the closer you are to the origin, your fortune may be more. Correct? So you are interested in not all possible sets, but these type of circles, because where it lands exactly is of not much relevance for you, because you are only interested in how much money you are going to win. And therefore, what matters is just this R radius. Okay. And now, what is your omega? So let us say that you have the unit, your omega is unit disk, set of all points in the plane, x, y in R2, such that, uh, so it's on this unit disk, so x square plus y square is less than or equal to 1. And f, okay, f is generated by all, so I just say generated by uh, uh, rectangles, open rectangles. You can write here by sets of the form. This type of thing we have seen before. Sets of the form A cross B. Sorry, I will not use A, but maybe something else generated by J1 cross J2. Yeah, contained in omega, where J1, J2 are intervals, and they could be, so I put here -1 to +1. But only those which are contained will matter. So, okay. Anyway, so let's not worry too much about F. Quite often, we don't even care to describe what F is, but try to understand this in an intuitive way. F is generated by small rectangular things. You can put open or close, it really doesn't matter. But I think it's good to put open. We should, I think, put open sets. Do this type of things. And then look at contained in, it doesn't matter where it is contained in. It may be in some closer to something, away from the center. It could be like this. So that's how your J1 and J2 are positioned, and then this is what you get. Okay, so now what is our P? Our P, I am not going to say this, but let me say, okay, so I should just say this, what it is on J1 cross J2, right? Let me just say it explicitly. This is area of this rectangle, area of J1 cross J2 divided by pi square. Pi r square. R is equal to 1, therefore just like pi. Okay, so that's it. Or more generally, if you have some funny region here, shaded portion, so P of E.
But here the dependence isn't on radius, it's uniform.
Yeah, sorry. Okay. True. So better not to. Yeah. Sorry. Yeah, good point. Thank you. So, yeah. We don't describe this. But as such, you can allow this, but you have to modify your
Probability function.
integral by means of some density. Let's not get into that. Sure, yeah. Okay. Now the what I want to say is, so your random variable x, okay, p is some suitable thing, okay, so that the total thing is actually r. Uh, volume will be 1. So p is some probability. Function explicitly told what it is. So, but what is this? And this is what I wanted to illustrate. So, x of a point x comma y is equal to x square plus y square under square root sign. So this is a radius. How far it is from the origin? So this is a distance from origin. Distance from origin to x comma y. Okay, P had, for the problem I described, you can write some complicated expression here. Let's not worry. But the point is to illustrate your what type of sets. So the role of random variable now I hope is brought out more clearly. Okay. Okay. You are not, yeah, your main concern is how far you are from the center. And that means that is brought out by this. Okay. Of course, you
So,
could also be interested for some other problem. We have seen problems of this nature. See, I showed you one problem in which you had this type of parallel lines equally spaced, and then you throw a needle, and for one of the calculations involved, what is the angle that this needle makes to this one? Okay, so it could be that you are interested, and why could be that type of thing. So in all these things, it's a bit complicated to write out everything most formally, but you get the idea of what a random variable is. Okay. So, uh, so let me say this.
so could you once explain what the problem was with what you wrote and then erased?
Which one? Here.
P J1 that
Okay. So,
area.
so what I am saying is, see, let me say this. I can discretize this problem also. Let me say what the problem is. So you see, you may have a board like this, dart board, and your aim is to hit the bullseye, which is at the center, of course. Okay. But if you are a very good marksman, you can throw a dart and it should land very close to the bullseye, if not exactly at the bullseye. Okay? And the level of difficulty decreases as you target to hit only the bullseye, but maybe it lands here. If you are a poor marksman, it can land here, or it may even go off the board completely, and in which case your fortune is 0. Okay, so that is the what you want to know is how much money. So you see, in this type of a game, if you hit within 1 centimeter, you may win rupees 10. Okay,
Okay,
if
sir, I get it.
you hit in this region more than 1 centimeter, but maybe within 2 centimeters, you may win 15 rupees. And
Yes.
sorry, maybe I should make it less, because to
So the
make it
throw is
realistic,
biased. It's
5,
not
and
random.
then maybe 3, and then 2, 1. So your fortune depends on how far you are from the center. And you can normalize everything and then make it into a unit circle, and then what you are interested in is this, and so on. Okay. Yeah. So that's a game. So within this disk, you may not really care where it lands, you can make a continuous game out of it or a discrete game out of it. So I said, I discretize the problem by saying, so distance from, this is a table that is of importance for this gambling game, distance from origin. So this may be less than or equal to 1 centimeter. This is 1 less than, so 1 less than, between, so let me write here, between 1 and 2, something like this. 1, 2, and then 2, 3. So somewhere you may want to add 2 because I discretized the problem. So here you add 3 and so on. So this may be 3, 4. Sorry, it's not aligned properly, but this is you 4, whatever. Sorry, open interval 4, closed interval 5. And after that, anything bigger than 5, you get 0. Or maybe you lose some money if if your dart lands here. That makes the problem more interesting. Anyway, so your fortune depends only on how far you are, and you can discretize the problem. This is sort of maybe more continuous model. You can also discretize it if you want, but this, you get the idea, right? Okay. So this is a realistic problem that one encounters. This type of board, dart game is common. Okay. Yeah. Well, so, okay, I have told you what is this random variable, why it is interesting or important to consider random variables. So, mathematically speaking, a random variable is nothing but a function from omega to real numbers, such that if you look at this set AX defined with respect to X, that must be an event, meaning that is something for which you can compute probabilities. Okay, that's all. Now, let me talk about this distribution function. So, distribution function of a random variable. Variable X. So let omega, okay. So I'll just say it a little more briefly. Let X from omega to real numbers be a random variable. Only word of caution, probably you will see this later on. You could, you know, why bother about mentioning this A, X and so on, AX belonging to F, because if you just write your function arbitrarily, it may so turn out that for some value of X, AX is not an event. Okay. And then you cannot talk about probability, and that is the reason why you need to sort of restrict your function capital X. So be a random variable. The distribution function function of X denoted, how is it denoted? Okay, F sub X, or simply F. Simply F, if there is no possibility of confusion. Let me just get more space. Is defined as the function f. So the domain is real numbers and the codomain is 0 to 1. What it does, okay, yeah. So defined as this is a function where so f of some x, this is equal to, you compute the probability of see let me write this here explicitly. Set of all, this is just ax, okay, ax, which is same thing as probability of yeah, so x less than or equal to x, or these spaces omega in capital omega such that x omega is less than or equal to x. Sorry, I just squeezed in and not enough space, so let me not scribble here. Everything will be clear now, but later when you read the notes, it may be confusing. Okay, so that's it. Okay, so yeah, this is a very convenient function. Sometimes it's called cumulative distribution function, but yeah, distribution function is quite acceptable. Why do we need to say this? Why not, if somebody may ask, why not just write, so why not f of x is equal to probability of x equals x? Okay, so it could be that this is always 0. This could be 0, 0 for all x, although, and so it gives no information. So, and hence gives no information about probability of ax. You are interested in probability of ax, but okay, so this is the thing. This is why it's important. Let me just say this. So in the example of this dart game, probability that you will hit any one particular, I mean, fixed radius. Your dart lands on a circle of radius exactly equal to r will be 0. Okay, because even the weighted measure for this, whatever probability you write, that will be 0. It's only for a region, that region meaning some open set, that it's going to be non-zero. Okay, so yeah, probability of it landing on a specific small set. You see, the circle is a small set, it has no area. Okay, so you should expect, at least in the continuous case, you should expect that probability of something landing on a circle of radius r is 0. Okay, pre-assigned specific value. But something landing on inside a circle of radius r, that you can always compute, and of course it will be positive for positive values of r. Okay, so that is the reason why you are interested in this. The distribution function is defined like this. Okay, so on the other hand, once you know probability of x, see, let me say this. So let me write out some lemma here. I want to say this. Okay. Is there something I want to say before I go to lemma? But I suppose I have done that. Okay. Yeah, let me just, even before I write down the lemma, on the other hand, one may obtain, even when it is non-zero, obtain, okay, the value of probability of x equals x. So which is same thing as probability of, so today I may write everything explicitly, but we should better get used to this notation, okay? Omega in omega, such that x of omega is equal to x. Okay, so get this from f of x. How? So note that so this set, the set x is equal to x is equal to ax minus union of ay, y is strictly less than x. Okay, is this clear? And now, so probability of this, okay, let us just do this little one. What is probability of union of ay? Okay, first of all, ays are all nested. Okay, therefore,
Sir,
probability of union of ay.
Sir, is there a countable union?
Very good point. So that's an excellent point. I want to say this. We will come to that. Okay, good. So let me write here. That's a good point. I better be careful here. So we may as well write this. Whatever I wrote is of course true, but you can read. The important thing is you can. I think it is better to first write like this and then explain. So before I go here, this is aside. So I write it in a different color. Union ay, y less than x is equal to union of a x minus 1 by n, and then n bigger than or equal to 1. So n going from 1 to infinity. So this is a countable union. Okay, so let us use this. This is equal to probability of union over so a of a of x minus 1 by n. Okay, here n goes from 1 to infinity. Yeah, you are taking away some positive quantity which becomes smaller and smaller, and this is of course nested. This is equal to limit n going to infinity, probability of a of x minus 1 by n, and which we may also write it as the same thing, limit y increases to x from below. Okay, sometimes people write here x minus. I like that notation, but the book uses this notation, so better you get used to book notation. P of ay. Okay, but what is this? This is equal to, it's more convenient now, limit y increases to x f of y. Okay, so therefore, what do you get? Therefore, probability of x equals x is just nothing but f of x minus limit y goes to x. Okay, y increases to x. Sorry. There's too much noise, but there's nothing I can do about it. I apologize for that. F of y. Okay. So this is what I was saying. Once you know this, and likewise, this you can try as a homework exercise. Maybe later on also this is given as a lemma. So let me first do this lemma. I will not do all parts of the lemma, but some parts of it. So distribution. The distribution function f is equal to fx. So I drop x after some time, okay, of a random variable x has the following properties. Following properties. Number one, so limit x goes to minus infinity of fx is equal to 0. Limit x goes to plus infinity is equal to f of x is equal to 1. Hardly surprising. B, whatever I just now showed here, okay. If x is less than y, then just 1 second here. This is, I hope I wrote everything correctly. Yeah, of course. Okay, no problem. If x is less than y, then fx is less than or equal to y, f of y. Okay, just because you have strict inequality doesn't mean that you must have strict inequality here. Strict inequality implies weak inequality, but inequality is preserved. So f is monotone. And C, this is an important property. I think I've already said this. No, maybe not. Let me write briefly. Limit h going to 0, h going to 0 through positive values, that is h decreasing to 0, f of x plus h, this is equal to f of x. That is, f is right continuous. Or continuous from the right. So, okay. Is there anything else I want to say? Okay, I can do many more properties just in one go, but let's not do that. Let us do some examples. First of all, I want to give proof of at least some parts of it. Yeah, so let us do A. Okay, proof A. So note that. So what is intersection of AX? Yeah, AX. All X. X in real numbers. The same thing as intersection of A minus N, N going from 1 to infinity. Okay. But let me just see what we want to prove. AX as X goes to infinity, minus infinity. And this is of course empty set. Okay. Why is it empty set? Is it clear? This consists of all those omega which are less than or equal to minus n for every n. Therefore, it is empty. That's all. Okay. Now, what about, let us write. So, likewise, similarly, union of an. So, union of all these ax. Okay. X in real numbers is also union of an. N bigger than or equal to 1. So, n equals 1 to infinity. That's a whole space omega. Okay. And now what do? So you take fx and allow x to go to minus infinity. Okay. If x goes to, so uh, 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 I will say that so if x goes to minus infinity, you see we have already proved that f is a monotone function. Did I do that? Maybe that's it would have been easier to first discuss that. But anyway, let me not say this. I have already started doing something. As x goes to minus infinity, f of x which is equal to probability of x less than or equal to x. Yeah, as x goes to infinity goes to, let me make it a statement, goes to limit x goes to minus infinity, probability of x less than or equal to x by definition actually. Yeah. This is because each one of these sets, so this is a definition and this is a nested sets, that's it. Okay. And this is equal to probability of, so an, so a minus n, and going from 1 to infinity, which is limit. Sorry. This is actually equal to, but next line I can write limit. This is equal to 0. Is that clear? That's all there is, nothing more. So you just write, in other words, so I could have started off. So this goes to what is the question. So I'm just saying, I'll write in symbols, limit x goes to minus infinity, f of x is by definition limit x goes to minus infinity of probability that x less than or equal to x. But these sets are nested, and so this we have seen before. This is equal to probability that the same as this limit is same as probability of this set which is obtained as intersection. Here you can do it in 2 steps, but I'm using this. So by this remark, so I'm using this. So that's equal to probability of the empty set. I can write here equal to probability of the empty set, which is equal to 0. So now everything is clear. So the proof for the other one is also similar. Similarly for limit x going to, plus infinity, f of x is equal to limit, let me write it, doesn't matter, plus infinity. Oh, I don't have too much time, so better rush. F of n is equal to limit n going to infinity. Probability of an, I could have written that, is same thing as limit n going to infinity. And these ans are nested, so sorry, there is no limit now. I can just write probability directly. Union of ans, that's P of omega, is equal to 1. And what about B? B is actually rather trivial. So I will not write the complete proof, but for the sake of completeness, I must just discuss the idea of proof. So suppose that I suppose, x less than y, then a of y is equal to a of x union the set, so set of all omega in omega such that, what is it? So x less than x omega less than or equal to y. Okay, and if you had any doubts, you can rewrite this like this: is equal to a of x union. Now you write ax complement intersected with ay, correct? And already it says, I mean, see, this says that because it's an event, complement is also event, intersection of two events is again an event, therefore this is an event, and therefore probability of ay is equal to, well, this already implies this is bigger than or equal to probability of ax, and that is f of y is bigger than or equal to f of x. And incidentally, it also tells you, okay, there's some, okay, that's not, yeah, this is perfectly okay, no problem. What about this one? Right, continuous. So I'll just tell you what is the relevant thing there. So for C, or proof of C, note that this A of X is the intersection of A of X plus H positive. And if you had any doubts, you can also write it as a countable intersection, X plus 1 by n bigger than or equal to 1. Try and do the same thing for X negative and it doesn't work with intersection replaced by union. There's a slight problem because this works, so because f of x is defined to be probability of, sorry, let us not, okay, so I don't want to say it in terms of this. This is because ax, so I can remove probability. Ax is equal to set of all omega in omega such that, yeah, so x omega is, the crucial point is you have put equality here. Equal, less than or equal to x. Okay. If you had strict inequality, this side would not be equal to this side. Okay, think about that. All right, I think that's it. That's all I want to say about the proof. And now let us go to the, let us do some examples because these are important. I have about 12 minutes. Let me do some examples. Maybe as a first example, we already discussed something. I work out the distribution function for those examples. How about that? Okay. So, suppose two coins are tossed and the outcomes are observed. Okay. So here, let's assume that the two coins are the same. See, for writing X, you don't need to really know P. Okay, for the definition of random variable, it involves only omega and F. Okay, whereas in order for you to write your this distribution function, you should also know F. So let us say in the first example, so let me write that here. Suppose that probability of H, so tail is equal to Q, probability of head is equal to P, and of course P plus Q equals 1. And of course, I'm not going to say P is bigger than or equal to 0, Q is bigger. I mean, let us assume P positive. Okay, let's assume that. So suppose that this is the case. So a coin is tossed. Coin is tossed twice. So we erase this. And X counts the X is equal to number of heads. Is that what I wrote? H tossed shown. Okay. So in this case, what is the probability? So F. Okay. So we need to write this AX before we can write FX, right? So we can just recap. What is FX? Fx is equal to probability of this set Ax. And of course, the value will depend on the numbers thrown. So the possible numbers are 0, 1, 2. So this will be 0 if x is less than 0. Moment x equals 0, what does that mean? No heads. That means you have tail. And probability of x less than or equal to 0 is same thing as probability of tail, which is q square. Okay. So this happens if 0 less than or equal to x until you reach 1 but not quite exactly equal to 1. So until x less than 1. Moment you x becomes 1, what is Ax? A1. I have already written A1. Okay. So I don't know if I wrote A1, but I definitely wrote the elementary events there, computed the values that x takes. So A1 will involve tail, HT and HH. So that means that so Q square plus 2 times PQ. One head and one tail. or you can say PQ plus QP, whichever way you say it. This is if 1 less than or equal to X, strictly less than 2. And the moment X becomes bigger than or equal to 2, you get the whole space and therefore it is 1. Not a surprise. This is it. This is your Fx. Okay. Yeah, if you have any doubts, you can ask me. I can quickly do the other one also, but let us understand this. Is there any question here? We can discuss that. Yeah. So this is number 2 in the the distribution function in of the random variable sum variable x that computes a sum. So let's just call this f. Computes the sum of the numbers thrown or numbers shown when a pair of fair dice is thrown. Oh, sorry, just something happened here. Something happened by mistake. Okay, got rid of it. The distribution function now is the verb, the main verb is. What is that? So some can take values. For want of time, I may be unable to finish it in 5 minutes, but let us do this carefully. So you know that I'm going to first of all tabulate it, okay? X can take values where X is the sum is at least 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so here there is only one way of throwing this, therefore it is 1 by 36. The probability of x is equal to little x. So I write here little x, not capital X. So this is 36, 1 by 36. This is, we saw already, 3 by 36. And you want to throw 4, so you must look at partitions of 4, the sum of two numbers. So 2 plus 2, 1 plus 3, 3 plus 1. So that is only 3 of them. So 3 by 36. And so on. You can fill it out. This will also be 1 by 36. The only way is 6, 6. And this will be 3 by 36. And so on. You can do this. But what is it that, so fx is going to be a little bit complicated. F of x, it will be, yeah. So let me say this, there will be so many possibilities. X can take values below 2, okay? So it will be 0 if x is less than 2. And of course, it will be a long list. So perhaps one should write the list in a horizontal fashion, not like this. But anyway, so I don't know how to write it in a horizontal fashion. Okay, let me just not write the whole thing, but because there's no time. Here it is 1 by 36. If 1 less than or equal to x less than 2, sorry, 2 less than or equal to x less than 3. Okay, and 3 by 36, if 3 is less than or equal to x less than 4. The moment it hits 4, you this yeah sorry this is I should add one more 1 by 36 also to that, because it becomes 4. You see, the sum must be at most 3, okay, or at most x, including x. But x here the sum takes integer value, so sum must be at most 3. So one is sum can also equal 2. Therefore, 1 is also a favorable event. So that becomes 4 by 36. And let me do one more. So
Sir,
4,
3 can only happen in 2 ways, sir.
yeah, 3 can happen in only 2 ways.
1 plus 2 and 2 plus 1. Right?
Okay.
Or am I
1
missing
plus 2,
something?
2 plus 1. Yeah, so this was wrong.
It's the same for 11.
Yeah, of course. So once that goes wrong, this also goes wrong. So this is what happens when I'm in a hurry. I make mistakes, so have to be careful. Thanks. Now you can list, after all, it's an elementary problem. You people know how to do it. And, favorable events, at most 3, therefore 1, 1, 2, 1, 1, 2. So that is 3 of them. Okay. And 4 less than or equal to x, strictly less than 5, but it takes only integer values. So 4. So if it is 4, I will have, 4 I can write as 2 plus 2, 1, 3, 3, 1. That's why it is 3 by 6. And then whatever previously I had 2, so this will be 6 by 36. You can simplify it later. But now you get the hang of it, right? So on and so forth. Mind you, it's always good to remember, when you make a mistake, you can correct it yourself. This must be a monotone increasing function. Okay, so that is the thing. And for this reason, actually, it's called the cumulative distribution function. There are many things to say about these things, but today I'll stop here because my time is up. I don't want to rush through and so on. So complete this exercise just so that you know you are able to do this type of calculations. You need some practice also. Okay, I stop sharing. Yeah, this time I'll remember to copy the link. Okay, the lecture notes was posted only this morning. Sorry, last time I completely forgot about it. All right, see you on Monday.
Thank you, sir.
Yeah,
Thank
thank